Start the recording. We're done with my chemistry labs because I started counting. Today we'll do a paper lab with a short lecture at the beginning on two-dimensional NMR. And then next week you're going to meet with me to pick a paper. Yeah. And that's all we're doing for lab next week. And then the week after that, you'll present your paper and we'll call it.
I thought we were going to have time where we look for things.
That's next Tuesday.
So we have 5.
I think it says 4, but yes, a handful. So the most broad papers will also be the most work. Typically, they'll be the easiest to understand, but there's going to be more volume because the most broad papers are what are called review articles, where it's basically like, okay, well, here's this topic that a bunch of research has been done on. Let me summarize it for you. And they typically have like hundreds of references, and they can be anywhere from 30 to 75 pages long. They're basically a chapter in a textbook.
Yeah.
Those are okay. If it's a relevant topic, you can do that. But I think it's more work than picking one that's a little bit more focused. Now, what you can do is start from one of those review articles and look and say, if they say something that seems interesting in the first couple pages, like, oh, and then you go find the citation that they are referencing and go to the original paper.
Yeah.
And that'll typically be more focused. Where most of the papers we should be looking for should be somewhere in the 5 to 10 pages range, not including supporting information.
Okay.
And references. That's typically the normal length for a reasonable paper. Maybe a little bit shorter if you get something from Nature, because they have to condense it and make it more broad. But so that's, if you see something significantly longer than that, that's probably not what you want. And if you see something that's much shorter than that, it's usually what they call a letter, and it's more like a, what I'm working on. Sort of, you could call it a paper, it's still a publication, but that's also not really in depth enough. So aim for that 5 to 10, maybe 15 page range. Quizzes looked, the first question looked good.
We've never done that way, programming. We always try to get to.
So this one looked good, other than from C, the deprotonated form. You both drew this. I assume you both worked together because you had the same answers, which is fine. But you both just drew it like this. Really, you want to make sure that there's a charge on there. But I didn't mark any points off of that one. The bigger problem was on the next one. And that was, you started from bromopentane, which means for all these ones that are pent, you didn't need to actually add any carbons to anything. So for all of yours, you started with magnesium followed by CO2, which adds a carbon, which turns them all into. So that would be right for B, and for D, and for F. But then all of the ones that are pent, there's a different pathway. So for pentanoic acid from 1-bromopentane, I would do hydroxide to an SN2 to make it 1-pentanol. Follow it up by dichromate in H2SO4, whatever acid it was. I think it's H2SO4 to give you the fully oxidized version. You didn't need to add another carbon and then and go that route. There's,
That one. H2S authority, H2S.
yeah, sounds right. But your general gist of it was right. You were just, for all, you did too much for all the ones that are penta.
I told you. I didn't think that had it in the first place. Well, then why would we use it later to add arguments? Because we used the R group with the iterating. That's what I, did we do all the other ones? Right.
Maybe I didn't look at them, because that doesn't sound right to me. So what I would do for, let's talk about the other ones.
There's a lot of our friends in all over the state. And this was taken in this other yeah.
Right, different pages, go back and forth, and not just reverse. So for hexanoic acid, I would do our starting molecule, Mg CO2 to get the hexanoic acid. 1, 2, 3, 4, 5, 6. Then if we're trying to get hexamide from that, so that's the answer for B right there. It's just magnesium followed by CO2. That's what we did in lab with our green earth reagent too, right?
That's it.
That's all you need to get hexanoic acid. Well, followed by a proton source probably. But yeah, so then for D and F are going to start the same way. Right, because once we get to hexanoic acid, so once we get to hexanoic acid, we can take our carboxylic acid and just all we have to do is apply ammonia to get hexanamide, which is D. Or if we're trying to make ethyl hexanoate, we just need ethanol in H plus.
And that's,
And that would give us that.
and what would give us?
So D would be just adding ammonia, NH3. That gets us F. All right, and pentanoyl chloride, we just do from the pentanoic acid. So from our result up here from A, we could take A, the answer from A, and just say SOCl2 to get pentanoyl chloride
C.
for C. I'm going in order alternating so that I can see the pence with the pence and x's with the x's. Obviously. Doesn't everybody think that way?
Yeah, I noticed that with alternating with Richter.
No, I was maybe just making a joke in my own expense because that is probably not the most relevant or intuitive way to think it through, but that's what I jumped in. So that would give us C, A followed by ammonia gives us E and A. Oh, that's it. There is no G. So there was a lot more writing on yours. I also would encourage you on these ones that are where it's sort of multi-step. They're kind of synthesis problems, they're a couple steps. It can be helpful to write it out like this so that you don't confuse yourself and try to cover too much on one arrow. Even if you then eventually turn around and rewrite it like this, thinking it through and showing your products kind of makes more sense like that.
Yeah.
Any other questions on these ones? That teal is still writing really nicely.
Is it erased?
Seen worse. I'm always worried about the lighter color, the brighter colors, because I never think they're going to show up well on camera. But they actually have been lately. It's a decent camera. All right. Yeah. You're both in decent shape still. You're both solidly in B range. And Taylor, you're right at the edge of an A. Riley, the good news about your midterm grade is nowhere to go but up because you're not going to do that like that again.
No, I know.
So I will actually offer two options. I'll offer them to both of you. So for a third of the points that you missed, you can correct your own test and turn it back into me.
Okay.
For up to a third, I'm still going to regrade it, make sure you did everything properly.
Yeah.
That you can get a third of the points you missed that way.
Like on the parts that you didn't already write correct answer on.
I don't think I gave very detailed feedback, especially mechanisms.
Yeah, like mainly mechanism version.
Yeah. There's a few where you made just small mistakes that I did it for you, but the mechanisms are going to be where there's the most room. So even on the ones where I told you what the right answer is, you go through it. I'll give you a blank test and just go through it and do it right. You can get a third of the points, or you can gamble. And if you do better on the final, I'll throw out the midterm grade.
It's very tempting.
You don't have to both make the same decision. You both get to decide that yourself.
Okay.
And you don't have to decide right now in front of me. Think about it. And let me know what you decide. We'll say if you're going to do the correcting thing, let me know by Thursday, and then we'll turn it in next Tuesday.
Okay.
But just something to consider. Those are both options that some of my professors gave me at various points when I had a test that I didn't perform as well on as I wanted to.
Yeah.
So I will offer you that choice as well. No problem. We've all been there before. And OChem notoriously, and mine was in OChem 1 in first semester OChem. We had 2 midterms in the final, and on the second midterm was the first one where we actually had mechanisms on it. And I studied it for a bit, and I thought, these mechanisms really make a lot of sense. I'm just going to logic my way through them on the test. And then on the test, I totally blanked and went the wrong direction several times and got something in the 60s. And
right.
I mean, at least it wasn't an F, but D is slightly better.
Yeah, no, it's totally, you were right there on most of it. You just weren't there enough.
I didn't study as much as I should have. And I back to 2 weeks that I was sick and like relook at that material really. And I should have, but I didn't have time, so I didn't. I was like, we'll see what happens.
Yeah, that happens sometimes to everybody. So I won't say don't stress about it, because now you put yourself in a position where you've either got to do more work or you've got to perform next time, but it's a reasonable situation to be in.
Yeah.
And good news is even with your score staying the way it is, you're solidly a B.
Yeah, that's true.
So that goes to the more assignments part.
Yeah,
The only thing that doesn't have any points in it yet is your research project. So as long as you do well on presenting your paper,
yeah,
that category is going to bring your grade up a little bit too. So
I'm fine for damn, like,
then you'll
be
be,
able to pull it up.
it'll be close. I haven't looked at the specific numbers, and the weights and where that'll fall, but it'll bring you something close enough, close to an A, if you do well. So keep it up, keep showing up. All is not lost. All right. The other quick question: do they become more intuitive? To some extent,
Okay.
it's a little bit. It's a little bit like writing out a sentence when you're in elementary school or writing a paragraph. Is it more intuitive to write a paragraph now than it was when you were in sixth grade? Absolutely. You always kind of still start in the same spot, but the patterns become more natural. The more you think about it, the more you do it. I don't have the mechanisms all memorized at this point, but I know what the patterns are well enough that I can put them together on the spot. Granted, you don't ever have to get to that level because you're unlikely to ever wind up teaching organic chemistry based on your career paths at this point. But it's something that I had to practice when I first started teaching too. I didn't come with a chemistry degree. I wasn't inherently good at mechanisms by the time I graduated. It still took practice after that. But if you ever do come across a situation where you were just going to try and figure it out
Yeah,
on the fly, just look at positives and negatives.
okay,
If there's something that's not carbons and oxygens, then you might have to worry about the orbitals and things like that. But if it's all just biochem and chemistry, for the most part, watch your charges, positives, subtract negatives, don't draw carbons with 5 bonds, etc. All right. Now we actually get to talk about alpha carbons. All right, so just to reiterate what an alpha carbon is. So they use this terminology more than just with carbonyl carbons, but this is where you most commonly see it. If you just hear somebody say an alpha carbon, generally they're talking about a carbonyl compound. But it does apply beyond just carbonyl compounds. If it's not a carbonyl carbon, we'd usually call it the active carbon. And we saw this when we were talking about elimination reactions, right? We had bromine that was going to get attacked by a nucleophile. We would call this the active carbon and call these the alpha carbons. So alpha carbons in general means one carbon away from the functional group. And then it keeps going down the Greek alphabet after that, with the exception that basically nobody knows the whole, not nobody knows. Chemists don't typically have the entire Greek alphabet memorized. But you know the first 4, alpha, beta, gamma, delta, more or less matches the English alphabet. Alpha is an A, beta is a B, gamma is a C, and delta is a D. What if you have a much longer carbon chain? Like say we're talking about a fatty acid that has 3, 4, 5, 6, 7. Let's just say it's got, I don't know, however many I just drew. A lot of times what you do if it's a much larger molecule is that would be the alpha carbon. But if we're really interested in what's happening at the end, we just go from the back of the alphabet. What's the back of the English alphabet? Z. What's the back of the Greek alphabet? No, that's just how English people pronounce Z. Omega. So an omega is the end of a carbon chain. And so if you hear about, actually I put this in the wrong spot. So if we have a fatty acid that is structured like this, that has a pi bond, 3 carbons from the end, we call that an omega-3. So if this is the omega, this would be omega -1. I think I had to go one further than that. But basically, you're counting from the back of the carbon chain if you're listing omega. But that's actually where the terminology in nutrition comes from. Omega-3 fatty acids means they're unsaturated in the omega -3 position, or omega-6 or omega-9. Unsaturated fatty acids is basically where is that double bond. Omega-3s and 6s mostly because our body can't synthesize them. And unsaturated fats are good for us because they get this structure in them that if we look at what the bond angles do, if it's saturated and all of these carbons are sp3, you get a long straight chain molecule. If it's unsaturated and you have all of the unsaturated bonds in fatty acids are cis bonds, which gives them this kink in their structure, so they don't lay as flat together, so they're less dense, and they also are more likely to be a liquid at room temperature. Things that are liquid at room temperature, fats that are liquid at room temperature, are better for us because they're less likely to clog our arteries. And they're better. Our cell membranes will preferentially use unsaturated fats so that our cell membranes remain more fluid and less rigid. And we can't make them ourselves. When our bodies synthesize fatty acids for the sake of energy storage, they almost exclusively make saturated fats. Most mammals make saturated fats, which is why eating fats from mammals tastes really good, but it's not great for us. Unsaturated fats have to be made from seed oils or fish. And so we don't get enough of those if we don't get enough of those from our diet, we start winding up with heart disease and hardened arteries, things like that. So it's an essential nutrient because, and they're also involved in, these omega-3s are one of the precursors for vitamin D. So you've heard that our body can make vitamin D on its own if we get enough sunlight. The other ingredient is omega-3 fatty acids, which you can actually track. It's really interesting from an anthropology standpoint. Cultures, the further a culture is from the equator, the more white, oily fish they have in their diet, traditionally. And that's because they see less sunlight, so their body can't make as much vitamin D without the omega-3 fatty acids. It does. It's just, but if you look, across the world, if you look at Scandinavian versus Japanese versus Inuit diets, the level of white oily fish that they eat is very, very high compared to cultures around the equator. So all that just to say, it doesn't stop there. We don't typically count past delta, but if you see omega, that just means we're counting into the molecule. And we've already seen this this mechanism where we look at a carbonyl. If we have a little bit of acid or base, we can convert it to the enol. And then the interesting thing about this, we've seen this step before. What we haven't really done much with is if we have an enol, we can do an addition reaction. Or an enolate is the deprotonated form of the enol. So basically, these alpha carbons are more reactive than typical sp3 carbons. It doesn't appear like they have a functional group on them. So normally we look at that alpha carbon and say, oh, it's just the CH3. There's nothing really we can do with it. Unless it's got a carbonyl one carbon away. And so the fact that it goes to this enol intermediate allows us to add things, to add nucleophiles in the alpha carbon position. So like we've seen in the past, under normal circumstances for both class 1 carbonyls and class 2 carbonyls, the ketone is going to be the form that dominates. So it might be more than 99.99% of the time for a ketone. However, there's a little bit of that enol form present. And if we happen to have a way to stabilize the enol form somehow, like via resonance, we can make that ratio go more like 10% versus 90% in the enol form. So this is if we have a beta diketone, so beta because the second ketone is on the beta carbon. This doesn't have any resonance in this one, does it? Because we've got an sp3 carbon in the way. But if we do an enol rearrangement, now all of a sudden we do get resonance between our two pi bonds, and it allows us to put a hydrogen in a spot that makes a hydrogen bond to the same molecule. So we basically have it stabilizing itself by providing itself hydrogen bonds if it's in the enol form.
The hydrogen doesn't really bond to that.
Well, the hydrogen's got a partial positive here, right?
Yeah.
And hydrogen's always got a partial positive. And the oxygen's gonna have a partial negative.
Right.
So it is somewhat stable because all we really did is when we did this rearrangement, this was our mechanism for it. If you have a little bit of acid around, the base catalyzed tautomerization looks pretty similar, just with the steps flipped, remember? So we can protonate that oxygen first. So it's not the same hydrogen that was attached to the alpha carbon. But once we protonate it, that gives us a carbocation on that carbonyl carbon, on the active carbon, which then can turn into a carbon-carbon pi bonds if we have another base around, take that hydrogen back, take the second hydrogen. So both hydrogens are still relatively stable. And the fact that we make something that has both the resonance stabilization and that has this partial positive, partial negative intramolecular force. Those are both things that are desirable, that are more stable. Right, so normal conditions, yes, our carbonyls are just going to stay as a carbonyl for the most part. If it's an aldehyde, then this ratio is going to shift to form the enol a little bit more. if there's resonance stabilization of the phenol form, then that's gonna make it even more likely to show up as the phenol. Because this is one example. Can you draw another molecule that, what do you mean?
Like, comes above the 7 to 9.
Yeah, so basically if we had a molecule that looks like this, that can go through a tautomerization. It would look like that, right? No resonance, resonance. This doesn't have that intramolecular stabilization with the partial charges, but it does have a whole lot more resonance by doing that, right?
Yeah.
So anytime that we can rearrange it so that the pi bond, moving the pi bond over gives us more resonance, is gonna allow us to favor the enol form a little bit more. And there's a couple different ways we can do it. I'm calling it on purple. That purple pen is done. Great, I'm gonna go steal another pack of pens because I like having fresh pens.
Is everybody using the big ones?
I think so, at this point. I don't know. I don't know what kind of monster would do that, but it's not. I'm not OCD about a lot of things, but my whiteboard pens.
Yeah.
All right. So we have the acid catalyzed tautomerization here. Just a couple of proton transfers moving those pi bonds around. Try and draw the base catalyzed version.
So we want to make it negative instead of positive.
Exactly. You have a base around, instead of giving a proton to our carbonyl beginning, we're gonna start by, we're probably gonna start by removing a proton. I'll give you a minute.
Oh, stop. The base we would typically use. See you.
Just use hydroxide. It's a good, if you're not sure what to use as a base, just use hydroxide.
That can't be right, it has to be considered as well. So, well, so like I said, giving it was, as. Just 130. Are we trying, it's the same product.
Yes. That's a good word, right? Yeah. Now watch it. It's not. And then it's just wrong. But I would. I would do.
We didn't use the hydrogen at first, runs for part of the active part.
Okay, so that's a valid. That's a valid guess as to what could happen, but that's not going to give you a photomerization. We have the hydroxide attached here. That's going to make a acetal instead. Right, so that will also be a competing reaction. So part of the trick with these mechanisms is don't just propose a step that can propose a step that happens that gets you closer to where you want to go.
Yeah.
Remember in our roadmap analogy? You got on the freeway going west when you needed to be going east. That's a valid way to get on the freeway, but it doesn't get you closer where you want.
Yeah.
So first step, hydroxide pulls off the hydrogen to make it negatively charged instead of positively charged. Which once again gives us resonance stabilized intermediate. And the second step is another proton transfer. Right, how do we feel about that?
I don't like that part of this.
We don't see that very often, right?
Right.
But the fact that it's resonance stabilized is what allows that. And it's also what leads to the next part here is even if we only have the enol present in small amounts, like 1%, less than 1% of the molecules if they're enol form, they're super reactive. They're very strong nucleophiles. they have a lot of electron density on that alpha carbon when they're in their enol form. So if this is our enol, we've got a lone pair in the allylic position to a pi bond. Which means we can have a resonance structure. What would the resonance structure look like for the enol?
The double bond goes to the oxygen and the oxygen pitches.
So if you can't really go the other way, the double bond can't go towards the oxygen because that oxygen already has 8 electrons. So lone pair is going to move towards the pi bond, and the pi bond moves away from it. So our resonance structure would look like it still involves putting a pi bond between the oxygen and the carbonyl carbon. But it puts a carbon, it gives you a carbon with a negative charge, which we don't like, in the alpha carbon position. So this resonance structure is a good nucleophile
Because the carbon.
because the carbon becomes a good nucleophile. So it's a little bit different. The only other time we've seen carbon act as a nucleophile have been Grignard reagents and deprotonated alkynes, right? Because we saw that as a nucleophile, and then we saw this effective, we draw it as a covalent bond. This is a very weak covalent bond, but there's a very strong partial negative on that carbon. So this just gives us another way to have a partial negative on that carbon, so the carbon can act as a nucleophile.
But it's not a partial. Negative.
Remember, this is a resonance structure, right? So really, it's both of these simultaneously. So even though one of our resonance structures has a full charge on it, we're mixing this resonance structure with that resonance structure. And which one would we expect to be the major contributor? The more stable of the two resonance structures. Yeah. So it's not even a full like half of a negative charge, because really most of the time it's like this. But a carbon with any amount of negative charge is a pretty strong nucleophile because carbons don't do well having negative charge. Right. And we see on the next page that is in fact exactly how it works. I don't like to fill these from the tap for the DI water, but I'm not going to get my keys out and go with the ladder.
Is there anything I'd want to leave that as 113?
Yeah, I could go. That's a good point. I could just go through there, but we've come too far. Yep. You ever have those movies or those TV shows that you don't even really like that much, but there's that one scene, one line that resonates with you?
Yeah.
To me, that's Harold and Kumar go to White Castle.
Okay.
There's a scene at the very beginning where they walk out their apartment door. And they take like 10 steps down the hallway and he goes, man, I forgot my phone charger. And Harold looks at him, we've come too far, so.
Yeah.
Hey. No, because I can vote after lab.
You want it?
No, I did not. What's up?
Do you want me to ask, go home to get my work packet and make like food for Dash for between doing anything on his game?
Mm-hmm.
Do you want something too? I'll make it myself.
Sure. Thank you.
Yeah, I'll make like a wrap or something so like you can have food.
Dad, he's just coming here after school, so we'll see him here.
Okay, yeah, perfect.
All right, so here's our resolution structure. So we just drew by names. Here's our next one. Let's practice drawing some enols. Two possible enols that can be formed from 3-methyl 2-butanol. And show the mechanism under base catalyzed conditions. Now I'm gonna go fill up my water bottle while you do that.
Just so much. Not that one.
Okay. I'm gonna draw it twice because we had two possible
Possible what?
enols formed. So that means because there's two,
Right, like the difference.
right? Because the whole thing with these enols is we take the carbonyl pi bond and it's gonna shift to one of the alpha carbons. It has to be an alpha carbon that has what though?
Partial.
An H. Because it's an elimination reaction, really, right?
Okay. Yeah.
So if we have a hydrogen there or a hydrogen here, either way, under base catalyzed conditions, our first step is exactly. But that can't happen if you don't have a hydrogen on the alpha carbon. So if this was 3,3 dimethyl, we wouldn't have two possible enals.
Right.
guess, since it says just to go to possible emails, like this was all makes sense, no.
Oh,
If it didn't say show the negatives, you didn't have to show the electrons.
okay.
You could jump straight to the final answer, which we'll see in a moment. So those are our two resonance structures, two sets of resonance structures. So final product. We're looking for a full credit answer on that. Got to be clear about the difference between our equilibrium arrows versus our resonance arrows, right? You can get away without having the resonance brackets as long as you're clear with your resonance arrow.
Okay.
So final product for the top one. And so out of these two possible products, which do we think is more likely? Why? So there's less there hindrance for the.
I didn't even.
So that's a good thought. How did we decide when we were doing elimination reactions? This isn't all that different than an elimination reaction, right? When we were doing elimination reactions, how did we decide what product was formed? It wasn't because of sterics. It was not Markovnikov, it was the other guy in his research group that had beef with him. Close. This would be the Hoffman product versus the Zaitsev product. So, for addition, Zaitsev was about elimination. So, and the reason that we go back to that is because the reason that the Zaitsev product, the more substituted alkene, is preferentially formed is because more substituted alkenes are more stable than the less substituted alkenes. So we're going to have some measurable amount of both of these, but we're going to have mostly the more substituted enol or enol.
It's preferred what?
Because it's more substituted, more sp3 carbons around an alkene makes it more stable.
Like, so the more substitute alkene is preferred
Because it's more stable. You have electron donating groups around it that are going to stabilize. Although now I'm thinking maybe the resident structure. Hold that thought, let's take our break and I'm gonna double check that.
Okay.
I may have just talked myself out of it. Let's take 10 minutes, let's come back at 5 after, and we'll clarify that. And go from there.
And it's crowded like Boston, the train.
Yeah. And I was just worried to get that after that, like, I. We got it, I remember that. Dad pulls up this, like, he's like, oh, that's what I. Playing, it's like, oh, yeah, yes, it's playing, attempted, and cascade. Those when I'm stuck. Oh, the woods to run and ownership. That's the woods. That place keeps being turned over as the woods, but they say to bring it back.
Yeah, that's really the next one. Yeah.
Yes. It's in there, I just have to hit publish.
Okay.
I don't think she does Friday, 26th, that's the graduation of her. But I don't think ours to read, but you can try to take it in. But now I'm ready for the. How's that? I've seen that off, they're not.
On camping ground through the bookstore, the marketplace,
You're like,
through student life.
you show. See that on this thing, you know, it's not. But I need my capture, I was like, great.
Gonna bedazzle it.
I'm doing, I was like, I didn't really know what to do, and I didn't want to just be like, oh, this is here, you and not. So I'm gonna do a silhouette of me during my solo, but like all the dust, like the background, the dazzle canvas.
Have you seen that that person on YouTube who's bedazzling their entire car?
Oh, yeah, I have. I didn't know it.
They're most of the way done with it, I think, at this point, right?
Yeah,
It's not one that we're following, but it shows up occasionally.
exactly.
Laura just puts on YouTube videos to put the kids to bed, because we usually
Right.
only have like a half hour before we have to go to bed at that point. Because when the kids get older, they want to stay up till like 10 o'clock with you, which is lovely. They want to spend time with us, but
That was always my time that I would want to like talk.
yeah, exactly. Which is, again, lovely. Does not leave a whole lot of time for like zoning out or like. Anyway, I did double check, Zaitsev's rule does apply to enols, so more substituted enols are favored. All right, let's talk about enolates. The enolate is basically a resonance stabilized intermediate that you just leave in that state. You don't put it back, you don't add the proton to it. So under basic enough conditions, this is actually pretty stable. This resonance structure is pretty stable on its own. It's actually not all that different than a carboxylic acid when you look at the resonance, right? If you picture replacing this carbon with an oxygen, it basically is a carboxylic acid. So enols are relatively acidic. They're relatively easy to pull that hydrogen off. Which means our resonance structures are going to look a little bit different too. Because our resonance structure for the enol looks like this. This is still okay, partially stable, but this is still very much the major contributor, the neutral version, right? Versus this enolate, we have a negative charge no matter where we put it. So yeah, putting a negative charge on an oxygen is favorable to putting it on a carbon, but at the same time, we're going to have a negative charge either way. That means both of these are pretty significant contributors. So would we expect that to mean that enolate is more reactive, or the alpha carbon, I should say?
I think so.
You think it's going to be more reactive? Yeah, because we got a stronger partial negative on that carbon.
Right. Because it's all like, something's always.
Right. And we're not putting a positive charge on an oxygen. Go ahead.
Do we do a step for the resonance or?
No, so if it's enolate, it stops there. Basically, under basic enough, because remember that the next step was you had to have a proton source
Right,
to be able to do this, right? If you're under basic enough conditions, you don't really have a proton source, or at least not many of them.
yeah,
So you can get it to stay in the enolate form instead of, so remember 8 just means that you pull off a hydrogen and it has a negative charge, right? So an enol that's deprotonated is an enolate. And so, yeah, you can get it to stay there. It's not going to be stable enough that we could, under normal conditions, unless there's some more stabilization happening, some more resonance or something, we're not going to be able to get it to stay that way like we could put it on the stockroom shelf.
right.
But we could definitely get it to exist long enough to characterize it to get an IR and an MR of it or things like that. Enolates are also what are called ambidentate.
Like ambidextrous.
Like ambidextrous, what does dent mean? Dental student.
Great question.
Means tooth.
Oh, really?
Yeah. It means it can bite from either side. So we refer to that for the most part as either an O attack if it attacks from the oxygen, or a C attack if it attacks from the carbon. But either way, we have 2 different places that have significant negative charge. So we have 2 different spots that can act as a nucleophile. All right, let's practice drawing the structure of an enolate.
During the attack.
No rush.
Why are you copying me? You have it in front of your face. I believe that's what I had in the position. And it's fun. So, reach you, oh wait. As our base.
Or just. Remember the trick, anytime we have a generic base, you can always just do that.
How can make it two, but then one spot for the base is three right?
Only one phenolate is formed, but it has two resident structures.
But it does. But it does. You're going to the left. And go to the right.
And once we know where those negative charges are in both of our resonance structures, we know what we can use as a nucleophile. I feel like the blue is already writing sulfate and erased so poorly. It's like I might not have even erased it. Anyway. All right, so if we want to make an enolate, we just have to look at what the pKa values are.
Are these something we should know off the?
No. They're useful, but you're not going to need to be able to recall them. I'll tell you on the test. And
Okay.
in a normal circumstance, you would just go look them up.
Right.
And so as soon as we just need to use a strong enough base that we can actually, if acetone, for instance, has a pKa of 19.2, we can't really use ethoxide as our base effectively because ethoxide's got a pKa of 15.9. And so we have a really rough idea of the size of these arrows. What's the difference between those two pKa values? Almost 4. No, 3.2. Isn't it?
Yeah, that's probably.
No, 3.2.
I just ignored the decimals, said almost.
Yeah.
Around, yep, approximately.
So that means that this equilibrium constant, we can actually have a rough idea of what that number is for the equilibrium constant, right? Between these two. For this reaction, the equilibrium constant is going to be something like 10 to the negative 3.3. I can do subtraction. 10 to the negative 3.3, or roughly, that's going to be like 3,000 to 1, 4,000 to 1 in favor of this domain. So less than 1% of our molecules are going to be present as the enolate. So if we can do both, we can do this, but if we have an enolate and we have the ketone present, what happens when we expose a ketone to a nucleophile? What was the first step you tried to do for the base catalyzed isomerization?
Active carbon, the active carbon, and then the double bond goes up to the.
So that's going to give us a side reaction if we're not careful when we make an enolate. What would our product look like then?
After the HCO.
After this attack. So we're going to have that.
Yeah.
And our second acetone molecule, our enolate, was attached there.
Oh, okay, I see it.
Counting carbons wrong. Right, so our alpha carbon from one acetone gets attached to the active carbon from the other acetone. And then if we clean this up, we have oxygen with a negative charge, 2 carbons attached. I did it again. That's not a whole lot cleaner.
That was better.
And so if we put acetone under basic conditions, we actually get a significant amount of this, which is still not inherently a very stable molecule because we still have this negative charge here. And it can still rearrange itself to be more like a diketone, right? If we move this down, we have to make, we can't really do that with this one, huh? Because we don't have a hydrogen we can take off. It didn't have the methyl group, but. So if we want to make an enolate in a way that's not going to make these other side products and it's not going to be reversible, we can do that. We just have to use a base that is going to give us a gaseous byproduct. So if we use sodium hydride, the hydride is a really strong base, grabs the hydrogen from the alpha carbon, makes hydrogen gas, which then leaves as a gas. And then that gives us this enolate that's pretty stable, or we have to use a nitrogen base, because those have much higher pKa values.
So we should focus more on like these ones that avoid byproducts rather than the ones for.
I mean, unless this is something we want to make for some reason. If our goal is to cleanly make an enolate that we can then use the nucleophile with something else. We don't want that first reaction.
Right.
So we either need to use stronger base. pKa of most of our nitrogen bases are in the 30s, right? So we don't necessarily just want to use sodium amide because then we could wind up with it attacking as a nucleophile, the active target. We want to attack base. We want to use a sterically hindered base. And this also doesn't apply if it's a diketone. Remember how we said a few slides ago, lots of slides ago, the beta diketone, where you have two ketones that have the same alpha carbon. These ones are really easy to pull that hydrogen off. pKa for this one is really low, so you can just use hydroxide if it's a beta diketone. And so here's our summary for enolates. If we use a strong but not too strong base, we get both of them present and they'll react with each other. If we use sodium hydride or LDA, lithium diisobutyl ammonium, we get our irreversible enolate formation and we won't have both molecules present. Let's do more practice.
I don't know, like, never got to draw food in the process and we just kind of did everything.
So do 21.6 and then we'll go over it and then we'll do 21.7.
I'm going to do more rest of it. So
Mhm.
There's 3 different, pages that put it, 5 different sets of documents to draw like the separate.
Is there one that's favored more than the others?
I mean, we have learned, no, the one that's in the middle, yeah, for both of them, like, they're not ready.
Right.
Both want that.
And it's doubly stabilized, right?
Yes.
This is the textbook example of a beta diketone.
Okay.
Beta diketones. This alpha carbon is way more acidic than either of these others because it's stabilized by both.
Okay,
So really, you're only gonna get one measurable product.
so we just have.
So just that.
Predict whether it's scheduled or not. Starting from. How would we predict that? We start already with their hours of reading or? So does it depend on the solvent?
It depends on the base. Sodium methoxide is not a strong enough base to pull off to make the enolate irreversibly, unless it's a beta diketone. So if it's a beta diketone or heavily resonance stabilized,
Well, it is heavily safe that.
so this one you're only gonna have enolate resonance.
But it's symmetrical. So drawing the end of the arms. You know, it's.
Correct.
So I'm just gonna go for the one that was. Upper right.
So for A, it's draw all resonance structures.
Yeah.
There's 3 of them.
Those aren't the same, the first and the last one.
They're not. They're the same for naming purposes, like we can't tell the difference between these 2 oxygens when we're going to name things. It's symmetrical, but for resonance structures, remember the electrons are moving so much faster than the atoms. Just like with our carboxylates have 2 resonance structures as well. It looks like that, right? Those are 2 different resonance structures, even though they're symmetrical, because the electrons move so much faster.
There's just two of us.
That's going to be urban, right? So is that. So is that. So basically, in this case, there's only two.
Okay.
And will there be a substantial amount of starting ketone? Why?
It's not as broad base.
Good. It's not strong enough to actually be pronated fully.
Like stuff on the right is called react. I think it's not drawn as like. Little.
When written start looking at C.
You cannot have. No.
Let's double check it because it's adjacent to a benzene ring, which means to think there might be some way we do it.
But that carbon will have five. There's so many parties.
Benzene always has resonance structures. It's next to a pi bond or a lone pair. You're always gonna have some resonance structures. And yes, these, we might not expect these ones to be as significant. They might not be major contributors, but they're gonna be there. And if we can put a positive charge into a benzene ring, we know there's at least two more of them, right? So out of all five of them, which is the largest contributor? Which one's the most stable?
And the one for the
maybe it was on the opposite side.
I would agree. Followed by this one. Then these are all approximately the same, right? They're all still there, though. They all still exist, which means that does give us a way to spread the electron density out over the entire molecule practically. So that is a pretty resonance stabilized enolate.
Yeah.
So would we see both or just one? So it's not as cut and dried as the beta diketone. But it's got even more resonance structures than the beta diketone did, right?
So that's just,
Just the enolate. Weirdest thing about teaching the same thing year after year is when you get really bad deja vu, you're not sure if it's actually deja vu or if I had somebody say the exact same thing to me last year.
I heard everyone calling my teacher next year.
Yes,
Oh my goodness.
I get the whole Gen Chem series and the Chem 100s.
Okay, that'd be nice.
There'll be a lot more students,
Well, yeah, that's true. But you're like.
but it'll be fresh. It'll be different. I'm gonna redesign the whole thing so it's like Bruce's ungraded approach. They won't have homework. They won't have quizzes. Quizzes will be optional. And they will just have tests.
Yeah, but that's how you learn.
So they're optional. They're still gonna be there.
They're fresh. I don't know.
I know, but I got really, really sick of grading AI garbage last quarter.
Yeah,
And a lot of people passed that shouldn't have passed because the way the class is structured to be forgiving that way.
right.
People that had a 45 on the final passed the class.
That's crazy.
So
So are you gonna do stars like Bruce, or are you gonna do like
it'll be
regular?
a little bit different. I'm gonna set it up so that they get multiple chances to do each one. They have to get it perfect twice. They're gonna get up to 5 chances per topic.
Okay.
And each lab also counts as a topic, so it's gonna be out of 30 instead of out of 20. And they have to get each topic that's assessed perfect twice. And I am not sure where I'm gonna fall on sig figs on that one, because I might say that they can count one of their two. They don't have to have the sig figs perfect or something like that, but
Okay.
so I think everybody's gonna be very mad at me next year.
Possibly,
And I'm gonna miss teaching OChem
yeah,
for
yeah.
the students that already know how to be college students. So D,
Yes, just started it.
guys, if you look backward one slide, it's already done for you.
I got to this.
Okay.
Because probably because we had to together one.
because the first one we do the same, even though it was a year.
But the thing is, you can't put the double bond to this side unless, well, it's different hydrogen. Because right now, this is. Versus. So if we drew the other resonance structure the other way. Remember, resonance structures can't change sigma bonds. Don't write this down. Because we don't like that. So no free resonance structures in this case. So what's different about A, even though it's symmetrical, is that it's lone pairs that are moving, not sigma bonds that are moving.
And you get both of this.
And so we would have both for these ones because there's not a whole bunch of resonance structures stabilized in the enolate. So we just get, we'll have the enolate plus. I looked at this more. I guess we can still, this is faster. 2,4-dimethyl 3,5 heptane diene. So heptane diene 1, 2, 3, 4, 5, 6, 7, 3, 5. Two, 4-dimethyl. 2,4-dimethyl. Versus 4,4-dimethyl.
Which is more.
Also, the other way of phrasing that is which one is easier to turn into an enolate.
Oh, the second. Right? No, you can't. First one. Because there's one hydrogen that they both agree on, and the second one doesn't have a hydrogen.
Bingo. There is no hydrogen that's alpha carbon to both of the carbonyls in the second one. So this one is super easy to deprotonate. And we would get, it's basically the same as A.
Okay. Yeah. What do I know? Did you do the method? No, but I don't have any either. Okay. Wait. So you look at two in the diagonal.
Yeah, there's no doubly stabilized alpha hydrogen on the first one. So the second. The house with a chimney and a cannon is not as acidic as the house with 2 cannons.
Yes.
And just for reference, just to start by drawing benzaldehyde. Acetophenone is just benzaldehyde with a carbon instead of a hydrogen.
The first one. That's the carbon, like the methyl group attached to it is as, like, that's what they.
The only alpha carbon in benzaldehyde is part of the benzene ring. It doesn't have a hydrogen.
Yes.
Versus the hydrogen, the alpha carbon here has a hydrogen, which then gives us all those other resonance structures too. All right, so enolates, little bit weird, resonance still tricky.
They're not that
No,
bad. They're just straightforward and.
we've laid a lot of groundwork with this. It's just getting good at drawing our resonance structures. All right, let's end there because I'm not going to start a new mechanism right now.
Sitting up for a second first.